Good morning. Today we will continue about topic the classification of crystals. The theme of lection, the crystallograph symmetry classes and Bravais lattice. Class or type of crystal symmetry is called a complete set of symmetry operation of this class. The further of division is the set of symmetry operations characteristic for a given polyhedron. All varieties of crystal symmetries of polyhedron and their physical properties are described by 32 classes of symmetry. Each of the 32 classes of symmetry is denoted by a special character. All characters are based on the theorems of the combination of symmetry operation, and each symmetry class has its own designation. For example, 2mm, 3m, 6 divided m, etc. What is it, the symmetry formula? The formula of symmetry is all the elements of symmetry recorded in a succession. In the first place, there are usually written symmetry axes from highest to the lowest. In the second place, the plane is of symmetry, then the center of symmetry. So the symmetry formula itself does not carry any information. But you can see a full set of element of symmetry if you write correctly the formula of symmetry of this crystal. For example, the formula of symmetry of the cube is 3 axes of 4 order, 4 axes of third order, 6 axes of second order, and the 9 plane of symmetry and center of symmetry. However, the symmetry formula itself doesn't carry any information. To decipher it, we must take into account the theorem of the combination of symmetry operation. There are a lot of theory of symmetry of combination, and it's rather difficult to remember that. But if you want to have the full description of crystal and its symmetry, it is necessary to use a combination of theory of symmetry, and then you can use the formula of symmetry for giving this information. For example, this formula of symmetry means that there are 5 planes of symmetry. However, the theorem number 4, along axis of the fourth order, only 4 planes can pass. Consequently, the fifth plane should be different from these 4, and according to theorem number 2, if there is a center of symmetry, it should be perpendicular to the axis of fourth order. International symbols of symmetry classes are much more compact, and by the writing of a character we can establish the mutual arrangement of symmetry elements, of course if we know the theorem of combination. These symbols are not all written but basic, the so-called trasmente, elements of symmetry. The latest are referred as planes. The symbols of Hammond-Morgan are spread. Look here, please, and you can see the symbols in according of the Hammond-Morgan system. N is axis or inversion axis of symmetry of nth order. M is the plane of symmetry. Nm is the nth order symmetry axis and n symmetry planes passing along it. N divided M is an nth order symmetry axis and the symmetry plane perpendicular to it. N2 is the nth order symmetry axis and the n-axis of the second order perpendicular to it, in according to the theorem number 3. Mn divided mm is the symmetry axis of the nth order and the m plane parallel and perpendicular to it, and can take the values 1, 2, 3, 4, and 6. I remember you that there are no the order, the axis, or more the fifth order in the real crystals. When using the international symbols, one must always keep in mind the theorems on the combinations of operation. For example, symbol NM means that the plane M passes along the axis of the nth order. According to theorem number 4, there must be n such planes. The symbol n divided m is the only plane perpendicular to the n, but by the theorem number 2, it implies that if n is beside the axis of the plane, there is also a center of symmetry. When you write an international character, it is extremely important to comply with the order of record. These rules are contained in special tables. In the international symbols, there are distinguished the coordinate elements of symmetry passing along the coordinate planes, and the diagonal ones passing at the angles of bisectors between the planes. This is taken into account when writing a character. If it does not comply, the meaning changes completely. Symbol M3, for example, means 4 axes along 3 bisectors or 3 coordinate planes of symmetry. According to theorem number 1, at the intersection of the planes there appear 3 axes of second order. By theorem number 2, at the intersection there is the center of symmetry. Apart from the symbols of Hammond-Morgan, there are used symbols of Schoenflies, Shubnikov, but they are less common. Now we must tell about the very important classification of crystal, the classification of Bravais or Bravais lattice. This classification based on the idea of the periodic arrangement of the centers of mass of material particles. In 1848, Bravais showed that the diversity of crystal structures can be described using 14 types of lattice, which is different shapes of unit cells and symmetry. These lattices are called Bravais lattice, and they are the basis for the classification of crystal by symmetry. Each Bravais lattice is a translation group that characterizes the locations of the material particles in space. Maybe C, B, or A. it depends on the arrangement of this atom. Here you can see C if this atom is located on here. We will take A, and on this face the lattice type of B. Body center here, it means that the central atom is located in the center of unit cell, and face center as here or here. This central atom is located on the center of face of each face of crystal. In a primitive cell, lattice sites are located only at the corners, and the complex cells are more similar sites. I is a single site in the center. Phi is at one site on each face, and base center CBA is at one site on the center of pairs parallel sides, here or face and back side. The unit cells of Bravais are the basic cells that are characterized by the crystal symmetry. By adopting one of the sides of the space lattice as the origin, that is for the site with the symbol 0, 0, 0, you can find all other sides of the lattice with the translational group, a set of a co-translation of the unit cell. The translation group for all types of cells in each symmetry is given in special tables. To highlight the structure of the Bravais unit cell, we must find the three shortest non-complementary translations ABC, and each translation must begin and end at the same sites. Next, you need to check the major requirements. The first, whether it is possible to build on these translations a cell that meets the rules of the Bravais cell selection. The second, whether all the particles of the structure can be obtained using a set of translations. And a system of coordinates of the sites belonging to a unit cell is called a basic cell. The entire crystal structure can be obtained by repeating units of the basic set of translations of the Bravais lattice. In this case, the origin is selected at the top of the cell, and coordinates of the sites are expressed as a fraction of elementary translations A, B, C. And at the end of our lecture, I want to show a short film about the classification of crystal, including the classification to Bravais lattice. Please. Thank you very much for your attention. Have a nice day.